Continuing with Packet 1 and functions. Here we analyze when functions are increasing, decreasing, and concavity. A function is increasing when the function rises from left to right. A function that falls from left to right is said to be decreasing. A function is called monotonic if it only increases or if it only decreases. For concavity of a function, the function is concave up if it bends upward as we move left to right. It is concave down if it bends downward from left to right. Here's an example. We want to find intervals of increasing, decreasing, and the intervals of concavity. So first, we notice from left to right, the function is rising, which means increasing. Then the function starts to go down from left to right, which means decreasing. Then it rises from left to right again, so now we can label the intervals of increasing and decreasing. So it increases from negative infinity to negative 1. The function also increases from 1 to infinity. The function is decreasing from negative 1 to positive 1. Now we want to find the concavity intervals. So here we can see where the graph bends downward, concave down, and where the graph bends upward, concave up. So the intervals for concave up looks like 0 to infinity. Interval for concave down looks like from negative infinity to 0. Another example. So just analyzing the graph where it rises from left to right, falls from left to right, and where it bends up or down. We can then label the intervals for increasing, decreasing, and the intervals of concavity. So the function is increasing from negative infinity to negative 3, as well as from negative 1 to positive 1. Intervals of decreasing are from negative 3 to negative 1, as well as from 1 to infinity. For concavity, we know concave up is where the graph bends upward. So here, the graph looks like concave up from -2 to 0. And for concave down, where the graph bends downward, the intervals are from -infinity to -2, as well as 0 to infinity. Here are some patterns with graphs. When you've done so many, they start looking familiar, called transformations. These patterns can sometimes be helpful when analyzing functions that may initially look complicated. An example. If you read this carefully, you may notice that this looks very much like a parabola, y = x squared. The difference is that some stuff is done to it, like the +1 at the end, 2 multiplied, and a -3 in the parentheses. So if we remember what the basic graph of y = x squared looks like, all the other stuff can be taken into account. So notice if I cover up the extra stuff, it really is the graph to the right. The +1 at the end just means that all the points on the graph to the right will go up by 1. The -3 inside the parentheses just moves the graph to the right by 3. So let's plot a key point real quick, the vertex. The vertex of the parabola is now 3, 1 instead of 0, 0. The 2 in front of the parentheses smooshes or shrinks the graph. You can see this more by plugging in values on a table. See? Pretty much looks like the graph above, just moved and smooshed a bit. Now we look at combinations of functions. In calculus, many rules are written as combinations of functions, so it's important to understand how to read it. Notice the two functions written here, one just a line and the other a parabola. Here, we're just playing around with the different combinations we can do with the two functions. Like adding, subtracting, multiplying, and dividing the two functions. One thing you may notice, which I didn't do here, is for each combination, analyze the new result and what kind of graph it may be. Also, analyzing what the domain of the function is, if any different from the first two functions. Here we look at the composition of two functions, plugging a function into another function. So, doing an example. I start with example C because it gives a general form and I can just evaluate example B quickly from it. For example A, notice it's the reverse of example B. And the result of A is different from B. Here's an example of looking at two functions on the graph f of x and g of x, and we can analyze the composition of them. Example A, we want g of f of 2, so we need to look at f of 2, which is 4. Then we have g of 4, and that on the graph is just 2. Example B, we want f of g of 0. So we look at g of 0 first, which is negative 2. Then we have f of negative 2, which is just 4. Example C, we want f of g of negative 1. And g of negative 1 is negative 3. Then we have f of negative 3, which is too far for this graph. But I know this is f of x equals x squared, so f of negative 3 is 9. Another possible helpful thing to notice when analyzing functions is odd and even symmetry. Odd functions are symmetric about the origin and can be tested by doing the following: f of negative x being equal to negative f of x. Even functions are symmetric about the y-axis and can be tested by doing the following: f of negative x being equal to f of x. In these examples, I am just testing to see whether the functions are odd, even, or neither.